The Diviner Lunar Radiometer on LRO has been mapping the moon since July of 2009. Some of the most anticipated observations we acquired were in September and October 2009, when the summer solstice occurs in the southern hemisphere of the moon. The LRO orbit is also aligned such that the plane of the orbit aligns with noon and midnight, and this allowed Diviner to measure the maximum annual temperatures that occur in the south polar region of the moon. Now, we had always known the south polar region would be a very interesting place to map. There are many large, rugged impact craters in that area, and because the tilt of the moon's spin axis is so low, there are regions in there that have not received direct sunlight for billions of years at the centers and insides of these craters. So what Diviner was able to do was to, for the first time, map the temperatures on the surface inside these craters, and it revealed some very interesting things. The first thing that it revealed was that the area is extremely cold. At the coldest spot that we measured inside the coldest impact crater was 29 degrees Kelvin. That's 29 degrees Celsius above absolute zero, the coldest that you can get. The temperature that the moon needed to be to trap water ice for periods of billions of years is on the order of 100 Kelvin. So there were regions that were significantly colder than are needed to trap water ice, and this is very exciting. The other thing that we noticed was that the area surrounding these cold traps were also very cold. We can determine this by taking the observations that Diviner makes on the surface and then matching them with a thermal model that can predict temperatures on the surface and below the surface. What we found when we fit the thermal models to the Diviner observations was that the temperatures below the surface were also very cold in regions surrounding the actual dark cold traps. We estimate that roughly half the surface area of the moon at latitudes poleward of about -80 south are cold enough to trap water vapor either on the surface or below the surface. So with Diviner, we discovered these so-called lunar permafrost regions, regions where there could be dry, illuminated soil at the surface and then underneath cold, frozen ground that could contain water. Now, the cold temperatures that we measured in the south polar region are also interesting from the standpoint of what volatile materials could potentially be there. Volatiles are substances that tend to be liquids or gases at room temperature. Each substance has a unique freezing or boiling point, and volatiles with high volatility have low freezing points. Volatiles with low volatility have high freezing points. So the maximum temperatures that Diviner observed were cold enough not simply to trap water ice, but also many other volatile compounds that have a volatility that's higher than that of water could also be trapped. This includes compounds such as ammonia and carbon dioxide. It also includes organic compounds such as formaldehyde or other simple organics that could be trapped at these cold temperatures. Now, Diviner has the capability to measure the surface temperature of the moon, but we don't have any direct ability within Diviner itself to determine its composition, especially the presence of buried ices. However, the LCROSS spacecraft, which impacted the moon on October 9th, 2009, gave us a rare opportunity to actually get some direct information about what's going on at and below the surface. What's exciting about this is that A, there was lots of water present, maybe about 5 to 10% water below the surface, and B, a lot of other volatile compounds were observed. So we have a very good agreement between the species that LCROSS was able to observe that were buried below the surface and those species that we would expect to be frozen at the temperatures that we observe from Diviner. Another thing we were able to do with our Diviner results was to explore the temperature history of the south polar region of the moon. Currently, the sunlight hits at a very glancing angle at the South Pole, and any relatively minor bump or crater surface causes a shadow that will become very, very cold. This hasn't always been the case. Earlier on in the history of the moon, maybe 3.5 billion years ago, the obliquity of the moon was up around 15 degrees, which is quite a bit higher than it is. Under these conditions, sunlight could stream directly into the shadowed floors of craters, causing them to be quite hot, and we would predict that no regions on the moon would be cold enough to trap water ice early in the moon's history. Gradually over time, as the Earth moved away from the moon, the obliquity of the moon decreased, and the first craters that could form permanent shadow were in fact steep, relatively fresh, younger craters that we also see on the moon today. Gradually over time, even shallower, larger craters became shadowed on their surfaces, and today, like Cabeus crater, which is one of those larger, shallower craters, those turn out to be the coldest places on the moon. However, these coldest places currently were not the oldest cold traps, which are still these sort of smaller, smaller, steeper walled craters. And so we might expect to find even older deposits of volatile substances in those craters if we were to sample them someday. The discovery of lunar ice adds one more reservoir of volatiles in the solar system that we now have to study. We know that the terrestrial planets like Venus and Earth and Mars have volatiles, and we're very interested in the general question of where volatiles come from on terrestrial planets, because this is, of course, the material that our oceans and atmosphere and life itself is made out of, and its origin is a very important prerequisite for life to form and evolve on planets. The question, what we don't currently know is exactly where all this water came from. There are many sources, and since the amount of volatile material on these terrestrial planets is a very, very small fraction of the total, secondary processes such as impacts, solar wind, and other things like that can have a big impact on how many volatiles and their nature and what happens to them over time. And so getting samples of volatile material from everywhere in the solar system, comets, asteroids, terrestrial planets, and then studying them in detail is a very important endeavor. The ultimate goal of this work is to find out exactly where all the volatiles on Earth, the ones that we're in fact made out of, ultimately came from and arose, and this will give us some insights into the potential habitability of planets around other solar systems as well.